Hello. So we've covered the fundamentals of what the theory of evolution is and is not, but let's refresh our memories really quickly before we move on, or carry this forward. So the three principles of evolution by natural selection. First, the principle of variation. Organisms vary. 2, these variations are passed from parent to offspring, so the principle of heredity. And 3, the principle of differential fitness. So not all individuals survive. Some are more fit. They are better able to reproduce because of their variation. The key part to this evolutionary framework, that very first principle, is variation. So therefore, we need to have a way to talk about variation. The language that scientists use for variation is statistics. Today, we will get those basics down to make sure we are all on the same page in our understanding of some key terms and key concepts of statistics. So before you throw up your hands and go, no, let me tell you, it's gonna be okay. Trust me, I'm a doctor. Okay, not a funny joke. Okay, but I do promise, this is not a statistics class. You just need to have a solid understanding of the concepts. Here we go. Let's start with the mental exercise of how to organize some variation. In this instance, we'll look at height. So you have this football field just packed with people. You want to get a sense of how much height variation there is in this sample of people. So the first step is to organize them, to categorize the people by height. So you ask them to line up behind a sign that indicates their height. So on the left, you have the shortest people in the group at 5 feet tall, exactly. And then we have a placard for every inch taller, all the way up to 6 feet 5 inches, way on the far right. When you organize data, or people, like this, you have created what we call a histogram. Now you'll notice that I included a count up in yellow of how many people are in this histogram, how many data points. This is indicated as N. N equals 160. And yes, I did actually count them all. Okay, the histogram here it's helpful, right? The height data they're organized really nicely. But let's add just a little more to it. What if you wanted to know how sex might be distributed in the variation in height in your population? You can code that too. So here, women have on white shirts and hats, and men have on blue shirts and hats. There is definitely overlap between them, but generally speaking, women are mostly over on the left side of the histogram, and the men are sort of mostly over towards the right. There's a lot of overlap though. Now, let's think about how we would organize or characterize the shape of the histogram. And in order to do that, we need to add some more terms. So first off, it would be really useful to be able to say what the most typical height measurement is, or what we would call the mean of the population. Okay, so we calculate the mean of the population by adding up the heights of all the individuals and then dividing by the total number of individuals, 160. So our first statistical term is mean, the average of all the items in a sample, which is represented by the symbol mu. Now when we add up all 160 heights and then divide by 160, since that's the number of individuals in our sample of people, we find that the mean is 5 feet 7.5 inches. Okay, good to know. So the average height in our study population, 5 feet 7.5 inches. But clearly there is a lot more going on here with the variation in height. What about the spread of the data around that mean? I could say that there are 8 columns on the left and 10 columns on the right, but that doesn't really give you a good sense of how the number of individuals sort of gradually diminishes as you move away from the mean. Are there lots of people all the way out to the edges? The same number in each column? What's the spread look like? Well, we need a statistical term to characterize that shape of the histogram. Or another way to say this is that we need a way to describe the shape of the distribution of data points around the mean. What we need to calculate then is variance. Variance is a measure of how spread out your data are. So just as you calculated the mean to get the average height of people in your population, you can calculate the average distance the people are from that mean. The average distance that they deviate away from the mean. So we would calculate this by looking at the height of each individual and then subtract that mean, the 5 foot 7.5 inches, from it, and then you have that distance, that deviation from the mean. And you add up all of those differences, divide by the number of individuals in the population, and voila! You have the average distance from the mean of the population. Or do you? Actually, there's a small dilemma. Since the mean is in the middle, half of those distances are going to be negative, and half will be positive. So if you add them all up, they cancel each other out, and you end up with 0. So instead, what we do is we subtract the mean from the individual height, and then we square it. And this way, you always have a positive value. So then you calculate the average of those squared differences. So let's put that into written words. So variance is the mean of the squares of the differences between each data point in a sample and the average trait value for that sample. And it is represented by the symbol sigma squared. So let's look at how variance changes for different variation. I cannot speak today. Let's look at how variance changes for distributions with different shapes. So here you are looking at what we call a normal distribution. Normal distributions have this really nice symmetric shape to them. So we'll call this one distribution A. Now, I'm going to add a couple of other normal distributions to the mix. What do you think of these? Distribution B is tall and skinny, and distribution C is much flatter. So the shape of distribution A is kind of somewhere in between. So do you think the variance of distribution B is larger or smaller than distribution A? Or what about distribution C? Well, the variance of distribution B is smaller than the variance of distribution A. The spread of the data around the mean is less in B than it is in A. So what about C? What do you think? You likely figured that one out correctly. The variance is larger. There is an increased variance in C compared to A because the data are more spread out from the mean. We actually have words to describe the shape of those two distributions. The one with decreased variance, distribution B, is what we call leptokurtic, and the one with increased variance, distribution C, is described as being platykurtic. Now, one of the things all three of these distributions have in common is that there's just one peak. The mean of the population is also where the greatest number of data points lie. These kinds of distributions are called unimodal. And this is not always the case. It is not always like this. There are also distributions with two peaks. These are called bimodal distributions. So what do you think happens to the variance in a bimodal distribution? Is this greater or less than the variance in a unimodal distribution? So it increases, yeah. So what do you think might cause a population to have a bimodal distribution for a trait? Now remember, when we talked about sexual dimorphism, remember we talked about how gorilla males are twice the size of females? So if you plot the heights of gorillas, you will get two separate peaks in the distribution. Now for humans, we only have 5 to 10% dimorphism in height. So as you saw with the people standing in that football field, where the women have on white and the men have on blue, there is a pattern to the difference between the heights of men and women, but there's so much overlap that it's still a unimodal distribution. Most people are in the middle because there's so much overlap between them. Okay, let's take the concept of variance and put it into algebraic form. Here is the equation to calculate a variance. The first thing you do is to calculate the mean of the sample, mu. Then you subtract the mean from each number in the data set. Each individual person's trait value gets the mean subtracted from it. You square the result so that you make the negatives positive, otherwise they'd cancel each other out. You want the distance from the mean, and it doesn't really matter which side of the distribution it's on. Then you sum up all of these squared distances, or a better way to say it is the squared deviations from the mean, as they are deviations from the mean. Okay, they're distances, but deviations is the better word for that. And last, you divide that top number, the summation, by the total number of data points in your sample. This gives you the average deviation from the mean. Let's walk through a little example. So plug in some numbers here. So we have some 1, 2, 3, 5 numbers. I've given you 5 individuals in our sample. So and these are the data points. X are the different data points for the different individuals. Sample size of 5, so n equals 5. Now we have the mean is 3.4. So what we're going to do is take that data point 1, the 2, subtract 3.4, and then we're going to square it, and then take the 4 data point, subtract the mean, and then square that, etc., etc. We're going to sum up all of those. And so here I'll just work out the equations. There's the subtractions. There I've squared them for you, and there we added them all together. And the next step then is to divide it by the number of individuals in the population. And so it's 11.2 divided by 5. So our variance is 2.24. 2.24. What does that number really tell us? Well, it tells us about the spread of the data in our sample. But what are the units for this? Well, it clearly isn't in the units we used for measuring our phenotypic trait because we squared it. So the number value of the variance it's kind of hard to conceptualize, isn't it? So we need to add in another statistical term here. Standard deviation. Standard deviation is the square root of the average squared deviation from the mean, or rather, it's the square root of the variance. So the standard deviation, it functions like variance, but the wonderful thing about standard deviations are that they are in your original units. So they are way easier to think about. So standard deviation is important because it tells you the dispersal around the mean in the units of your original data. Okay. So for a normal distribution, where you have that nice bell curve with no right or left bias in the distribution of your data points, one standard deviation includes 68% of your data, and 2 standard deviations includes 95%. 3 standard deviations includes 99.7%. Now, do you remember when I told you about the new species of monkey I named, Kusaracolobus hafu? Those specimens, they looked a lot like a monkey that existed 500,000 years before, but the hafu specimens are 3 to 4 standard deviations away from the mean of the older sample. They're a lot bigger. Now, if we plotted them on a histogram, they would be way over in that teeny tiny tail of the distribution, way to the right. Now, when the data points are that far out, we say that they are statistically different. Let's add another concept, statistical significance. This is a measure of how much evidence we have against the null hypothesis. Now, in the instance of the Kusaracolobus hafu monkeys, the null hypothesis is that they were not different from the older species. As the researcher, you need to decide at what distance from the mean of the known population you want to draw a line. Where are you comfortable saying, yes, these are the same species, or nope, extremely unlikely to be the same species? Well, most people choose either a 95% confidence or a 99% confidence. And you can see these two options plotted here. If your unknown data point falls out in the tails of the distribution, so here for the 95% confidence, or here for the 99% confidence, we would reject the null hypothesis. So rejecting the null hypothesis with a significance of 0.05 means that the unknown specimen is 1.96 standard deviations away from the mean, and rejecting the null hypothesis with a significance of 0.01 means that the unknown specimen is 2.57 standard deviations away from the mean. Now for those Kusrakalibus hafu monkeys, those were 3 to 4 standard deviations away from the mean of the older species. And therefore, I felt confident rejecting the hypothesis that they were the same species. And so, I named a new one. Now, I want you to do some figuring out here. Now remember, the mean is 5 feet, 7.5 inches, and the standard deviation is 3.8 inches. So looking at this distribution, how many people are greater than 2 standard deviations away from the mean? Okay, so hit pause on the video and work it out. Do 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 do. Annoying, I know, sorry. I always thought it was annoying in lecture when in the lecture hall when I did that too. Okay, so let's look at this. This is 1 standard deviation, and this is 2 standard deviations. So did you answer 4? Those 4 guys standing on the far right side of the histogram? If you did, you got it right. Okay, after you've kind of felt good about yourself, or you've gone back and tried to rework it and figure it out, I want you to think about this for just one moment. At a 95% confidence interval, we would have rejected the null hypothesis that those guys are humans. Now, you always have to approach statistics with a cautious mind. Just because statistics tells you something is significant, that doesn't always mean it makes biological sense. As we move into our study of variation, our populational approach to human variation, there are 3 things to keep in mind. The first is that the distribution tells you what is the most common value for a phenotype in that population. An individual near the mean for one phenotype could well be 3 standard deviations away from the mean for another phenotype. And no individual is the universal ideal for that population or species. Now we have the language to talk about populations at one point in time. We have that done. Now what I want to do is turn and add in a time dimension to this. So our next step is to start thinking about populations in a dynamic sense. This gets us into evolution. And populational thinking about evolution is the recognition that populations evolve, not individuals. Remember Lamarck? He said that individuals evolve. In evolution by natural selection, the range of variation in a population, it shifts over time. So to learn about the forces that make the mean of a population shift over time, I now send you over to the info page on shifting means, i.e., the forces of evolution.